Today I have the pleasure of having Professor Chris Juhlin from Uppsala University, and as part of this MOOC course on distributed acoustic sensing using fiber optic cable. And Chris would take us to the world of VSP and tube waves. Chris, stage is yours.
Okay, thank you, Alireza, and thank you for inviting me to present some notes or ideas on DOS. But the name of the lecture is VSP, tube waves, and DOS, and you might wonder why I'm mixing in VSP and tube waves when I'm supposed to be talking about DOS. But we often use DOS to record in boreholes, and if we're recording in boreholes, we're generally doing some kind of VSP, and we generally have to deal with tube waves. We've often thought of using fiber optic cables and boreholes, lowering them down and getting data very cheaply and very quickly. But we pay a price for this, and that is we often record tube waves instead of maybe the body waves that we're after. But we can also use the tube waves themselves to investigate the nature of the rock surrounding the borehole, which I'll show in this presentation. So I'll first say a little bit about what is VSP for people that aren't familiar with it, and then why we do VSP, and then discuss tube waves and show some examples with hydrophones. In a way, hydrophones behave in a similar manner as a loose hanging fiber optic cable. And then I'll show some examples from DOS, both good examples and some examples where we don't quite get the data that we want, but we can still somehow use it to learn about the rock and also about some of the caution you must take when you're using DOS. And just a final summary. So VSP is a term that commonly refers to seismic data acquired in a borehole with a surface source. But there are many configurations or many geometries you can use. And when VSP was first developed, the source was located very close to the wellhead of a vertical borehole. So the waves propagated mainly downwards or in the vertical direction, and therefore the name VSP, which implies a vertical seismic profile, as opposed to what we do on the surface, where we have more of a horizontal seismic profile. But there's many types of VSP now, and VSP is a general term. It should maybe be called rather borehole seismic investigations than VSP, but VSP has managed to stick around. And if we look at the case where we have a source on the surface, we'll have a zero offset VSP, which is sort of a classical VSP, where we have a vertical borehole and the source is very close to the wellhead, and so we're mainly looking at vertically traveling waves. Then you can have offset VSP, where the source is offset from the wellhead. Multi-offset VSP, where you have many sources and recording these sources at many locations in the borehole. Sometimes it's called walkaway VSP. And then we can have 3D VSP, where we have a grid of sources on the surface. So we don't necessarily have to have the source on the surface. We can have the source in the borehole and record on the surface, and then we have something which is generally referred to as VSP. And we can have the same geometries as above. We just exchange the source and the receiver locations. So this some graphical examples of what I just mentioned with the zero offset P, the source very close to the wellhead, mainly vertically traveling waves, offset. The source is offset, and therefore we get reflection points spread out along a horizontal reflector. When we have the zero offset VSP, nearly all the reflection points are at one location on the reflector. So with the offset VSP, we're able to map this reflector away from the borehole, the geometry of it. If we go to walkaway VSP, we essentially many offset source points, and we can get a more well-defined image of a reflector and better coverage than with a single offset point. And if we go to the 3D VSP, we're getting an aerial mapping of the reflector, which is intersecting the borehole, or a reflector even below the bottom of the borehole. And VSP can also be used when we don't have vertical boreholes. We can apply these geometries to boreholes which are drilled at an angle, or boreholes which are directionally drilled to go horizontal. And but we have the same objective to image reflectors intersecting the borehole, or reflectors below the bottom of the borehole. So I think I've explained why we do VSP already, but borehole data are the meeting point between geophysics and geology, I would say. And if we want to understand both the geology and the seismic data, we need to know where the reflectors intersect the borehole. This allows us to constrain the source of the reflectivity. And I would say that it's especially important to integrate VSP studies with velocity and density logs and the core if it's available, if we want to truly understand what generates the reflections that we observe on the seismic section. So if we do a VSP survey, a very important point of it is we are measuring the travel time directly from the surface to the receiver location. So this gives us an accurate vertical velocity function and allows time to depth conversion of surface seismic data. And I'll show you an example later on where this turned out to be quite important. We can identify reflectors in the borehole for correlation with surface seismic data. We can map reflection horizons away from the borehole. Another important point is that if we generally have quite a lot of attenuation in the near surface, and with the VSP, we only have the waves going through this attenuating layer one time, so we're able to acquire higher frequency data, and this allows more detailed images of the subsurface. And we can also predict depths to structures not yet drilled, both broadside of the borehole, that is off to the side, and also below the bottom of the well, below total depth. So, very quick overview of what VSP is. Now, the other word in the title, tube wave. So what is a tube wave? Well, it's a wave that's propagating up or down in a borehole. And classic tube waves are often observed in the boreholes. We can also observe higher modes, but this depends a bit on the rock properties and the source frequency. And the fundamental tube wave mode is often called a Stoney wave. But if the tube wave is essentially a solid liquid interface wave, so the term Scholte wave is more appropriate than Stoney wave. Regardless, I'm going to call them tube waves in the remainder of this talk. And they're generally a nuisance in our borehole measurements. They mask reflections and other arrivals that we want to see. We can reduce their occurrence if we can get good coupling to the borehole wall. If we can press our geophone or our fiber optic cable against the wall, we can try to put ditches between the source and the wellhead. This will reduce the amplitude of the Rayleigh wave, which is I'll show later or in the next slides here that the Rayleigh wave often generates the tube waves at the surface. We can use baffles. These are obstructions that we put in between our sensors in the borehole and attenuate the tube waves. Or we can do high density recording that will allow spatial filtering. And here's maybe where we can use DOS effectively since we do record at high density there. So the general or tube waves are often generated where we have a surface wave hitting the wellhead. This surface wave then generates tube waves that propagate downwards in the borehole. we can also generate tube waves when a P wave hits the borehole at depth. So we don't necessarily just have to have the tube wave generated at the surface. They can be generated really anywhere in the borehole where we have heterogeneities along the borehole or in the borehole itself. So here's some configurations for tube wave generation. We have here the direct tube wave coming down this dark black line. This was generated at the surface, but then we have our P wave first arrivals coming in, and at certain locations in the borehole, tube waves will be generated there. So over here on the right-hand side, we see some examples of how these tube waves can be generated. So this is the one I mentioned earlier, where the surface wave hits the borehole, and we get a tube wave propagating downwards. But if we have a P wave hitting a zone in the borehole where there's a porous zone with permeability, then you'll get water flowing in and out of the borehole, and this will generate tube waves, both an upgoing one and a downgoing one. We can generate a reflected tube wave where we have a change in the diameter of the borehole, and we can even generate tube waves where we have changes in the rock properties that surround the borehole. So we can calculate the velocity, the expected velocity for a tube wave in an open hole. What I mean by an open hole, this is a hole that's not doesn't have casing in it. There's a similar formula for casing. It's a little bit more complex though, but the tube wave velocity does not change that much with casing. So we have the fluid bulk modulus. This is the fluid in the borehole. We have the rock shear modulus. So this is the rock surrounding the borehole. We have the borehole fluid velocity, and we have these formulas for the bulk modulus and the shear modulus, which are dependent upon the relative velocities and densities of the media. So if we plug some typical numbers in here for the hard rock environment, we get that the tube wave velocity is about 95% of the borehole fluid velocity. And if we have a typical borehole fluid velocity, say water, we have velocity of 1450 meters per second and fairly competent hard rock. We then get a tube wave velocity around 1400 meters per second. So this is what we should expect in the hard rock environment for our tube wave velocities, something on this order. So here's an example of generation of tube waves from a mining borehole. We have now, we don't have fiber in the borehole, now we have with hydrophones. This is a zero offset VSP here on the left-hand side, and we have several locations where the P wave is coming down here, and we see tube waves being generated. The blue line here represents where we expect to see a reflection. You can see that the tube waves are masking any sign of this reflection, even if it was present. Same if we go to an offset VSP, we have the first arriving P wave here, and we have the tube waves being generated pretty much at the same locations as on the zero offset VSP. I guess I should mention when we're looking at this, we have depth increasing in this direction here, and time increasing downwards. Note this tube wave here, this strong one, it goes down the bottom of the borehole somewhere around here, and we get a reflection off the bottom of the borehole. Here we have good geophone coupling. We have a strong P wave traveling down a vertical borehole. But even with this good geophone coupling, we still have some locations where we have weaker tube waves being generated, probably due to where we have fracture zones. So I'm going to start talking a bit about DAS now, but I want to mention first about instrumentation. we've been using this instrument here, a Terra 15, and in contrast to most interrogators, I think that has been mentioned in the course so far, this system, it works a little bit differently. It measures the velocity along the fiber optic cable and not the phase. So most interrogators send down 2 pulses, and they have there's a gauge length, so to say, between these 2 pulses. And what's interesting is the change in the gauge length between the 2 pulses along the fiber. With the Terra 15 interrogator, only 1 pulse is sent down, and the position along the fiber of this pulse is measured. So it's a bit different principle, but we're still using a laser to send down a pulse along the fiber and looking at what is being returned. And from the velocity, the strain rate can be calculated. We have here the measured velocity or the vertical velocity, and we have the velocity of the rock here. So from measuring the velocity with the Terra 15, we can then do a calculation of the strain rate after the data have been recorded. So we can modify the gauge length after recording, which sometimes can be an advantage. We don't have to determine it from the start. So we have the change in distance along the fiber optic cable, dt or del t dt, and then we have the strain rate here, which we calculate with whatever gauge length we happen to choose, or we can also calculate the local velocity of the fiber along the fiber by applying this wave number filter in the wave number domain, where we get then a response which is maybe more typical to a geophone response. So what price do we pay for doing this? Well, we're not very good at recording low frequencies with the Terra 15. This is a signal to noise ratio which is fairly constant for phase-based interrogators. For the treble interrogator, there's very high noise level at frequencies below somewhere around 15 to 100 hertz. But as we move over this crossover point, 50 to 100 hertz, we have much lower noise levels. So if you're interested in recording high frequencies, then this is a good system. And this is one of the reasons we invested in it, since we were looking at using it in dam studies where we have frequencies of 2,000 to 4,000 hertz being generated. The treble is also a little bit better on picking up signals which are not traveling or traveling off vertical. The sensitivity is better at these higher angles than the phase-based interrogators. So we're want to now compare a bit with hydrophones, what we get when we record with hydrophones and what we have when we record with fiber optics. So there's a relationship between the pressure in the borehole and the phase velocity. If we have a harmonic guided wave, we can calculate the strain rate by taking the spatial derivative of this wave, and the pressure is equal to the impedance times the velocity of this wave, and the impedance is equal to the density times the velocity of the tube wave. In this case, this is the impedance of the fluid in the borehole. So we can eliminate the velocity here and get an expression for the change in pressure with time, and that ends up being equal to the impedance of the fluid in the borehole times the phase velocity times strain rate. So there's a clear relationship between the change in pressure to the strain rate. And we can calculate the pressure by integrating this equation. And we get this equation here in the frequency domain, which describes the relationship between pressure and strain. And this can then be transferred into the time domain where we're for the pressure and the strain. We still have here the impedance as a function of frequency as well as the phase velocity. These may be different depending upon what frequency we're dealing with. So this is a hydrophone survey from Japan, and we have this situation here where we have a P wave hitting a porous zone. Fluid starts flowing in and out of the borehole. We have up and down going tube waves being generated, and we see there's some very strong tube waves being generated, both upgoing and downgoing. And here we have a velocity log showing both the P wave and the S wave velocities. You see there's a lot of variability here. It's a hard rock environment, but the velocity varies extensively, and the strong indication that there's a lot of fracturing in this rock. And we have an especially low velocity zone down here, quite deep in the borehole. So downgoing P wave hits the borehole and generates tube waves. And one can set up a model to describe what the amplitude of these tube waves should be if we know something about the material properties or the media properties. In the elastic media in the rock, we'll have downgoing and upgoing waves that are propagating within the rock. You'll have different waves propagating within the porous zone, and you'll have a downgoing elastic wave. In the fluid in the borehole, you'll also have upgoing and downgoing waves above the fracture zone and below the zone, and next to the fracture zone. So I'm not going to go into the details here, but just want to say that you can develop a model which describes how these waves behave and what amplitudes to expect. And this is what these authors did. They set up a model here with reasonable estimates of the permeabilities and the elastic constants. And they had a finite difference solution, and they had a more simple theory that they wanted to use to give a more direct estimate of what amplitudes to expect. And in particular, they're putting in 1 Darcy for the permeability of the layer and about a 30% porosity. And it turns out that this more simplified theory for the upgoing and downgoing waves matches well what the calculations from the finite difference modeling show. So this simplified theory can be used to say something about what kind of permeabilities you can expect in the fracture zone without actually having to go downhole and measure them with pressure tests. And the ratio curves, they depend upon the permeability. So here we have a frequency on this axis, and we have amplitude on this axis. And this is where the amplitudes from the calculations plot. So by seeing where they end up here, we get an estimate of the permeability. And we see also that the higher this amplitude ratio, this is the amplitude of the P wave that's arriving, or the reflected tube wave compared to the P wave that's arriving. So we see that the higher this ratio, the stronger the P wave or the stronger the tube wave amplitude is, the greater the permeability is. So we get here a pretty direct measurement of the permeability in these porous zones. And they've looked at the amplitudes in the of all the tube waves that are being generated as we go down the borehole, and one then compares and done some modeling of the pressures to expect, and one finds that you need to introduce these permeable layers to better match the amplitudes that you record in the borehole. And what kind of pressures are we recording? Well, the pressures are quite low. They're on the order of a Pascal. So I went through this to just see what these pressures, what they correspond to in strain rates or in a borehole, to see if we could do the same thing with fiber optics. So we have here the formula for pressure, strain, and then the change in pressure with change in strain. And if we're 1 Pascal is about equal to a strain of about 4.44, or 0.5 Pascals is about 10 to the minus 11th. So at 150 hertz, we're looking at strain rates on the nanostrain level. And yes, so we probably could do the same thing with a DOS cable. So I'll move on to DOS now. We have some examples here we're going to look at. First, I'm going to show where the cable has been cemented into the borehole. This is the ideal case, and then we'll look at the case where there's where we have a loose cable. The cable's just been lowered into a borehole and is retrievable. So this is the kind of examples that are generally shown in when people want to promote DOS. On the left-hand side, we have DOS where this cable has been cemented in, and on the right-hand side we have data recorded by a geophone, and the two are pretty much the same. We have some optical noise here on the DOS. We have more tube waves on the geophone, but we see all the reflecting horizons on the DOS data that we see on the geophone. So the two are pretty much equivalent to one another. So very, very nice example of what you can do with DOS if you cement in the cable. Here's another example. This is from Australia, where they have a geophone, a cemented in fiber optic cable, and a loose hanging fiber optic cable. The geophone and the cemented in cable, they give pretty much the same response, similar to what we saw on the previous slide. The loose DOS, the response there is quite different. There's a significant downgoing tube waves here. There's tube wave reflections, but they do also see these P wave reflections that were observed on the cemented in or on the geophone, and signs of it on the cemented in DOS. They say this is a P to S converted wave, but I don't think so. If we look at this is a tube wave which is being reflected, and the slope of this tube wave is pretty much the same as this slope here. So I think this is actually a downgoing tube wave that was generated at some fracture zone in the borehole or porous zone. Here we have a walkaway VSP in Japan. Fiber optic cable is cemented in. So they had a number of shot points along this road here. there's a borehole here where they recorded in with DOS. Actually, they were recording in two boreholes, but we'll only look at one of the results. And we see as we are close to the borehole here, we go further and further away. The P wave is arriving later and later as we go further away. This is the DOS recording. This here represents the geophone recording. And at least according to the arrival times of the waves, the response is very similar. The geophones are maybe a little bit better as we move further away, but still, I think that the DOS looks very nice here compared to the geophones. So these were all, yeah. One more slide on this, showing that now that the data have been transformed into what we would call a VSP CDP transform. So what you're looking at now is something that would correspond to a surface seismic section. And we have again we have the geophone here. We have the DOS where the data have been binned in the same way as for the geophone, and here the binning has been more dense to try to increase the resolution. And we see that with the DOS data in this case, we're better able to map the reflectors away from the borehole. And if we bin even at higher density, we produce a better image than what we're capable of doing with the geophone. So here I would say that the DOS is outperforming the geophone. Okay, now let's move to some other examples, but with loose hanging cables. And this is mainly more what we're able to do in the academic world. It's maybe not so often that we have the money to cement in our DOS cables, either behind casing or that we sacrifice a borehole with cement. So I'm going to show here an example from Gotland, Sweden. This was part of an investigation into evaluating some formations for CO2 storage. So we had both 2D and 3D acquisition, a very small scaled survey. We're looking at about 1 kilometer across here. And we have this rather sparse 3D. This is the fold map of the 3D. And we have a longer 2D line coming down here. So we had two boreholes here within in the 3D survey, NORA-1 and NORA-2. And we performed the 3D survey. The boreholes were already in place, but they had not been logged with geophysically, so we didn't have any sonic or other logs in the boreholes. But we once while we were doing the 3D survey, we also put a loose hanging fiber optic cable in both of the boreholes and recorded along the fiber optic cables in conjunction with the 3D survey. And just to show, the slide is maybe a little bit out of place, but I just wanted to show that we had the core. These logs were recorded later after the initial processing of the 3D. And this shows the initial processing or the initial depth conversion of the 3D compared to the sonic logs. And we see we have a strong increase in velocity here. We should be getting a nice strong reflection from this area here, but instead it's coming in deeper. And this was puzzling us when we were doing the processing. Why we don't get a good match on the process or the depth converted section with what we expect. The depth conversion was done using the normal move-out velocities. This was the only information we had at the time for the depth conversion. So this is how we did the DOS. As I say, just very simple. Went down as far as we could in the boreholes. They were both about 800 meters deep, but we didn't get down to the total depth in either of them. So here's from Juhlin. That's this borehole over here, and this is a near offset example of a DOS recording. We got down to about 470 meters. We have a marked change in the character at about 170 meters. And that, I believe, is due to that the borehole was cased down to 170 meters. So this pattern that we see here is due to that we're recording within the casing on the fiber optic cable. And once we get below the casing, we get a different character of the response when we're in the open hole. We do see a nice clear P wave first arrival on this section, and we also see the strong tube waves coming down here. Some signs of a upgoing and downgoing tube wave being generated at this point here. This is an offset gather from the same borehole. Again, the clear P wave. We see the casing response, and here we see clear tube wave reflections being generated by the downgoing tube wave, and this tube wave reflection here that corresponds to where the P wave is also generating a tube wave reflection and a downgoing tube wave. So we have here the potential to look at what the character of these zones are that are generating the reflections. Maybe do a similar thing like was done in Japan to calculate the permeability of these zones. We do have downhole hydrological tests which we can compare with. So this would be a nice study, but it hasn't been done yet. There's the three reflections I'm talking about. Okay, if we look at the other borehole, which is quite different in its response, here we were able to get down to 730 meters, so we have almost the entire borehole covered with DOS. But the response is quite different. This is a near offset or zero offset, if you want to say, fiber optic recording, and it's dominated by tube waves. We don't even see the first arriving P wave, and it's really not much use even after filtering. You don't see the first arriving P wave. And we wanted to get an estimate of the velocity, vertical velocity for our depth conversion. So this wasn't so useful. But if we move to an offset point, we can make out the P wave arrival. But we also see that there's many points where we're generating both upgoing and downgoing tube waves when the P wave arrives. So we can, even if we don't see the P wave arrival clearly, we can calculate the travel time to a certain depth in the borehole, down to about 550 meters. So using these points where the tube waves are generated, we calculate a velocity of about 3,100 meters per second. And this 3,100 meters per second, it's considerably lower than our normal move-out velocity that we used for stacking, which is about 3,500 meters per second. So there's something going on here. Normal move out, these are flat-lying reflectors. Normal move out should be pretty accurate. Velocity doesn't change very much, but we have a normal move out velocity of 3,500 meters per second, and we have a downgoing tube wave velocity of 3,100 meters per second. Yeah, this just shows the same seismogram moved out at linear moved out at 3,100 meters per second. So we see that this very much agrees with the estimate of that we have. So the borehole logs again. The green are the actual logs. The blue is a 5-point boxcar filter of the logs used for calculating synthetic seismograms. We have what we could call the cap rock down to about 500 meters. Then we have a strong limestone, or we have a limestone which gives this strong increase in velocity. And then we have a series of sandstones and shales going down. And it's these that were actually of interest for the investigation. Now when we look at the sonic log, we see that it's a little down to 500 meters. It's around 3,100 meters per second, maybe a little bit greater than that. So we can take our sonic log. We don't have any sonic log information above 170 meters. So we use the DOS velocities. And we can then calculate a synthetic seismogram from the sonic log. And we can then compare with our 3D seismic data, and we see that they match quite nicely. And now we want to depth convert again. So here we have the depth conversion on the left that we initially did using the normal move-out velocities. And here we have the depth conversion using the DOS velocities. So when we depth convert with the DOS velocities, we get a very nice match here. There's this strong reflecting horizon corresponds to this hard limestone. And down here we have the Precambrian basement, which should essentially be transparent. And we see that this agrees well with what we have in the borehole. Whereas here there's a strong mismatch between what we see in the borehole and what we have on the seismic. So what this implies is, since the normal move-out velocities don't agree with the vertical velocities, this implies that at least the upper 500 meters is anisotropic. So I went through the stratigraphy already. I don't think I need to go through this again. So this now is an example of this of a shot section from the 2D profile that I mentioned earlier. This is the raw data here, and here we have the data high pass filtered to which allows us to see maybe some better these reflections here, although you see them even in the raw data. It removes this surface waves to a certain extent. And here we have a P to S converted wave coming in here. So I'm going to use this as a comparison with what we can get from modeling. So just to show, though, if we apply a normal move out of 3,500 meters per second on the left, then this strong reflection becomes flat. And if we apply the 3,100 meters per second normal move out, then this curves upward. So if we use the DOS velocity for processing, we're going to get a bad image. We need to use the actual normal move out velocity that gives a flat horizon if we want to get a good image. So again, the seismograms raw and filtered. So I'll just run through quickly some a seismic modeling of these to try to simulate what we see in the actual data. So I'll start with simple acoustic layers, but then add a fast surface layer. Again, sorry, not again, but then move on to having a gradient in the upper part. Continue with an acoustic one, but with a thinner fast surface layer, then move over to an elastic model using the sonic velocity, and then I will introduce anisotropy, and we'll see that it's possible to pretty much match what we see on the seismic. So this is just a very simple acoustic model. We have the first arrival coming in here that we see here, but we don't see this strong diving wave at all. And we see the reflection from this limestone here, which has the high velocity. But the move out on this reflection doesn't match what we see on the actual seismogram. So this doesn't work very well as expected. If we introduce a hard or a fast upper layer, this doesn't help very much. If we introduce a gradient, it doesn't help very much either. And if we put in a thin surface layer, it makes things even match less. So we need to go to an elastic model. And when we introduce an elastic model, then we start to pick up this diving wave, so to say, but it arrives much later than what we see in the actual data. We still have this first arrival here at near offsets, and the reflection is coming in too late still. We now have a surface wave since we have an elastic model. So that doesn't work. If we now use the sonic velocity to build our elastic model, assuming some relationship between VP and VS, it gives something which starts to look a bit more like what we actually record. But again, this diving wave is coming in too late, as is the reflected wave. So what we need to do is we need to try to get these more horizontally traveling waves to come in faster, and we do that by introducing anisotropy in the model. So here we have an anisotropic seismogram here, where the horizontal velocity is about 15% faster than the vertical velocity. And then we have this diving wave is matching very much what we have on the actual seismogram. We have the reflected wave also arriving pretty much as we expect or matching what we have on the seismogram. And even this surface wave looks like what we see on the seismogram, as well as this P to S converted wave here. So from the DOS, we were able to determine that we had anisotropy, and when we introduce this anisotropy, we can model our shot gathers quite well, I would say. So that's just the vertical velocity on the left and the horizontal velocity on the right. Okay, so this is a bit hands-on here. 2 cables. You want to feel them? Which one bends easier?
Blue one.
The blue one bends easier, yeah. So we did a test at our test site not far from Uppsala using these 2 cables in a shallow borehole. So these are the two cables for you that are online. And we want to develop a system here using downhole cables to record data. So this is what we got with our blue cable. And now we have depth increasing in the vertical direction, and we have time increasing in the horizontal direction. And here's a velocity log from this borehole. The borehole goes down to about 120 meters, but the cable only went down to about 100 meters. And when I first saw this, I saw, wow, look at this first arrival, beautiful. Well, this is in a hard rock environment. It's quite fractured, but we're looking at velocities on the sonic log on the order of 4,000 or 5,000 meters per second. And if we look at the arrival times here, that we have this arrival coming in at 2,200 meters per second. And we have what's presumably a tube wave reflection coming in at 1,300 meters per second. So I was quite puzzled when I first saw this. If we calculate the shear wave velocity of the surrounding rock using our formula for the tube wave velocity, we can back out what the shear wave velocity should be. We calculate the shear modulus, and we get this formula here for the shear wave velocity, assuming that we have this density ratio here. And that gives us a shear wave velocity of 2,050 meters per second, which I think is fairly realistic given that the rock is fractured, and we have P wave velocities on the order of 4,000 or 5,000 meters per second. So that seems to be quite okay, the tube wave velocity that we're measuring. But what about this velocity that we see here on this arrival that comes in so nicely? Well, this was the blue cable. This was measurements which were made on the same day with the black cable, and the black cable is stiffer. And here we have velocities, or here we have from a shallower hydrophone survey, and here we have from a geophone survey that we did not on the same day, but at different times in the past. It's rather odd that on the hydrophone survey we get 1,100 meters per second, which for what I think is a tube wave, but I'm not entirely sure. On the geophone survey, we pick up a weak first arrival here coming in at 4,500 meters per second, which is most likely represents the velocity, the seismic velocity in the surrounding rock. So what about this DAS black cable measurement? 3,000 meters per second. Same day. The only thing different is that we had the blue cable in here, we had the black cable in here. So the conclusion is that this represents a wave propagating down the cable. So, and I wasn't aware that you could have such strong waves propagating down the cable, so they pretty much mask all other arrivals, even the tube wave arrival. And this is a bit worrying if we that we can get such high amplitudes on a cable on a wave propagating down the cable. And the reason this one propagates faster is because the black cable is stiffer than the blue cable. So I think this explains it. And when I looked in the literature, it does turn out there are other examples of what we have with these cable waves propagating down the actual fiber optic cable. So this is something to be aware of. Now, we have here the loose hanging cable, the blue cable with these two velocities. We can since we have a very nice coherent arrival here, we can filter out this arrival using velocity filtering. Before I say that, I also want to say this is the expected arrival time for the P wave. So we're completely being masked by the cable wave, and even with filtering out this direct arrival, we don't see the P wave arrival. As you saw in the geophone data, even there it's quite weak. Okay, so this is removing the direct arrival from the cable wave. Now we see clearly the direct tube wave going down. Here's our reflected tube wave again, and then we see a reflected tube wave here coming from about 50 meters depth. If we look at the downgoing tube wave and the upgoing tube wave, and we see where they intersect, that's exactly at the bottom of the borehole. The borehole was about 120 meters deep, so that makes sense. Then we have that tube wave reflection there coming off some zone at about 55 meters, probably related to this low velocity zone here, which has higher permeability. Okay, so after looking at our data and doing some investigations on the literature, I found this paper here where they also have a loose hanging cable. Now this is in a borehole that was deviated, so the cable is maybe not hanging. The cable is in contact with the bottom of the borehole, since the borehole is deviated, and here they get better coupling than what we've had in our vertical boreholes. But you see there's zones where there's a lot of noise coming in and waves appearing to bounce up and down within some region here. And this here is a zoom of this region here. And they attributed this pattern that we see here to a wave just propagating up and down within the cable. You see that the slopes of these rivals here, they're less than the tube wave slope. So it's not tube waves propagating up and down. It's actually a wave propagating up and down the cable. Now they managed to be able to filter out this noise, and we're able to get a fairly decent looking VSP profile out of it. So this is the data without the filtering. This is the modeled response, so to say, of the cable. And this is when they subtract the model response from the raw data to get something which looks quite nice in the end, where the reflections can be traced much better than on the original data. So this was my presentation. I'll just summarize here. Tube waves are generally always present in VSP data. The better coupled the sensor is to the surrounding rock, okay, I missed, or to the surrounding borehole, the lower their amplitude. Inserting a fiber optic cable into a borehole presents itself as an inexpensive method for acquiring VSP data. I think we shouldn't be too optimistic if we just drop a cable down a borehole and expect to get VSP data that we can use directly for imaging. It requires quite a bit of work, and we may not get any useful data in the end. In vertical boreholes, the coupling of the fiber will be generally poor. We're better off in deviated boreholes with the cable resting on the downside of the borehole. In addition to tube waves, we can also have cable waves that produce unwanted signals. Tube waves do give us the potential to allow hydraulic properties to be investigated. So they shouldn't just be treated as noise. They can give us some information. And we get the best results for investigating the surrounding rock if the cable can be cemented in either behind casing or in the borehole itself. But this adds a significant cost, and we don't always have the funding to do this. So, thank you.
Thank you, Chris, for such a great lecture on tube wave and DAS.